So in the last class, we started our discussion on McCabe-Thiele method. Okay, and we said that this method is simpler than the previous one, and we had one very rigorous assumptions that molar flow rates of liquid and molar flow rate of vapor remain constant in the respective sections. And then based on that assumptions, we derived the operating line equations for the stripping sections and for the rectifying sections. And we said that the two operating curves on y versus x diagram are linear straight line equations. They intersect at certain points. Okay. Then we talked of now we have to make what you call a balance or a species balance or energy balance on this feed trace. So we'll talk about what do we call Q line. Essentially, we start with again y versus x diagram. We have xd top product compositions, and we have xw bottom product compositions, and we had one operating line for the rectifying sections, straight line having some intercept and slope. Similarly, we had another equation for stripping sections, a straight line, a slope, and an intercepts. Now what we'll do in today's lecture, we will obtain the equation of feed line. What do we call Q line here? All right. So with that introductions, let's get into this McCabe-Thiele method and complete our discussions of drawing the operating lines on y versus x diagram. All right. So we continue with this McCabe-Thiele method. Okay. The first thing, just note down that we have all L1, L2 same as L. We have all G1, G2 same as G, and similarly we have L bar and we have G bar for enriching section and for stripping sections. Okay. And we had operating line equations yn plus 1 as R over R plus 1, where R is the reflux ratio, xn plus xd over R plus 1. All right. And we did say that R over R plus 1 one can show as L over G. So this is the equation of enriching section, operating line, enriching section. Similarly, we have a straight line equation for stripping sections. Here we have L bar and L bar minus W bar xm minus W over L bar minus W bar xw. So n signifies the number of plates in enriching sections and m signifies plate number in stripping section. All right. And if we draw these two operating lines on y versus x diagram, so we have this 45-degree line and we have y versus x equilibrium curve given from Rawls law, etc. We mark this xd top product, we mark this xw as the bottom product. Then the equation of two lines is a straight line here with an intercept xd over R plus 1 and the slope as R over R plus 1. So we have this equation here. Similarly, we can draw the equation for the stripping line to show that this also is a straight line with the slope here given as L bar over G bar or L bar over L bar minus W bar, and with some intercept, etc. And we said that this line passes through 45-degree line where y equal to x, and similarly this line also passes through y equal to x line where we have y equal to xt. All right. What we like to do now that we have this feed composition xl. So we are interested in finding the equation of this line. That's called feed line. All right. And feed line is obtained and if you make a species balance and we make energy balance at the feed tray. So let's do this. Introduction of feed. So we are looking at this plate at which feed enters. So just above this plate, feed plate we call it, we have F molar flow rate of feed, and it has a composition ZF. We have the liquid arriving from the top plates, we have HL liquid, and let's call it F minus 1. So F stands for or signifies the number of the feed plate, and then we have G, and we have H, G, F, so it originates from F phase, and we have here L bar. So notice this change in the molar flow rate because of this F introduced, L bar, and we have HLF, and this vapor which arrives as molar flow rate G bar. It has a specific enthalpy H, G, F plus 1. All right. So we are trying to make species balance or mass balance on this feed plate. Now this feed can also have, it could be a mixture of liquid and vapor. So that's also possible. Feed could also be saturated feed at the bubble point, or this feed could also be saturated bubble at the dew point. So several combinations are possible. One most general could also be GF, separated in feed is separated into vapor. So some vapor compositions, and we have HGF, specific enthalpy for this vapor phase, and it's a mixture of GF plus LF with XF, and we can have HLF. All right, so several combinations for feed is possible. Let's start with this general case where the feed consists of vapor as well as the liquid with the composition YF, XF, HGF, and HLF as specifications. All right. So what we do now is the balance. So F plus L plus G bar. So F, L, G bar. Arriving at this plate F will be same as L bar plus G, the two streams leaving this stays. Right. In McCabe-Thiele method, we said that energy balance is not required, but this is the only place where one has to make this energy balance, enthalpy balance. Right, just like we did in case of Ponchon-Severett methods. Otherwise, our discussion for McCabe-Thiele method is almost complete with Y versus X diagram. This is the only place where we make this energy balance. Okay, so let's write it. F, we have HF plus L, HL, F minus 1 plus G bar, H, G, F plus 1. So all the energies of incoming streams 1, 2, 3 we marked will also be same as the total energy leaving that plate F. So we have L bar, G bar, H, G, F. Okay. Now, of course, we say that F can also be decomposed into GF and LF. So we'll come back to this later. Let's just work on this total molar flow rates of the feed as F, and this has a total enthalpy, specific enthalpy as HF, which can also be written in terms of HGF and HLF, etc. Okay. Now we make one assumption here that since the temperature drop across two consecutive trays is not very large, is not very significant, one can assume that a specific enthalpy HLF minus 1, a specific enthalpy of the liquid arriving from plate F minus 1 is same as HLF, the specific enthalpy of stream leaving this plate F here. Of course, you must understand the total energy of this feed is different from this. What assumption we are making is only thermodynamically, that is specific mole, calorie per mole for this tray, and this tray is almost same here because the temperature drop between the two plates is not very, two consecutive plates is not very significant, very small here. So this one is assumption here. Similarly, HGF is same as HGF minus 1. All right. So or HGF plus 1 here. So this specific enthalpy is the same. Of course, the enthalpy of this stream total energy of this stream and total energy of this stream will be different. So this is the thermodynamic assumptions we are making, realizing that the temperature difference between the two consecutive trays is not much. So with that assumptions, one can write this equation as L bar minus L HL. So this will equal to G bar minus G Hg. So saturated enthalpy of the liquid for the temperature for the feed tray, and the saturated enthalpy of the vapor of this saturated vapor for this feed plate temperature is Hg here plus F Hf. So all F minus 1 or F plus 1 we have approximated for this specific enthalpy here. So the second equation is written like this. So maybe 2 prime here, and then equation first and 2 bar we can write as L bar minus L. We divide same as Hg minus Hf over Hg minus HL. So we have this ratios. So let's look at this feed plate. We have F, we have L, we have L bar, we have this G, and we have this G bar. So all we are writing here L minus L bar, right, over F is shown to be equal. So this is your molar flow rate. The ratios is shown to be equal to the difference between Hg minus Hf. All right. Same ratios of Hg minus Hf, same as Hg minus HL. All right. Whatever we have this saturated enthalpy for the liquid phase and the vapor phase for this feed tray. So we have these ratios. We call this ratio as a Q. So this is the first time we are using this nomenclature. We are calling it quality of feed. We will see the significance of this. Essentially, this first term, if you recognize, all it means fraction of molar feed flow containing liquid. All right. So you should be able to recognize that this Q will assume different values depending upon quality of the feed, whether this feed is 100% saturated liquid or 100% saturated vapor, or it consists of some components of liquid and vapor. All right. So just for the discussion, if feed is 100% saturated with respect to this temperature here, liquid as a liquid, then no component is vaporized here. So whatever L bar is, we have L plus F, Q will be 0. All right. Similarly, if entire feed is saturated vapor, the entire vapor we get into this, we have Q equal to 1. All right. So this Q is called quality of this feed here. If you go by this definition here, Hg minus Hf over Hg minus HL, one can also write that it's a ratio of heat required to convert 1 mole of feed from the HF condition, conditions to a saturated vapor. All right. So we are saying that how much energy is required to convert this feed, to convert 1 mole of feed from HF to Hg. Okay, divided by the molar latent heat of vaporization of saturated liquid. So this is Hg minus HL. And of course, let's reiterate our assumptions that we said that the temperature across these two trays is not very significant, to the extent that we can assume that specific enthalpy here of these two streams, not the total energy, the specific enthalpy of these two streams, or the specific enthalpy of these two streams arriving and leaving, they are the same. So we wrote all those HLF same as HLF minus 1. All right. So this is calorie per mole. Now the total calories, because molar flow rates are different here as the feed is introduced. Okay. So this is a definition for G. As a consequence, now that definitions, you can write G bar minus G as F Q minus 1. You can also write as L bar minus L as Q into F. All right. So this is the same, one and the same. So this is these are the equations from which we can give physical meaning of Q here. Quality of feed. Q assuming 0, Q assuming 1, etc. We'll come back to this a bit later. Let's say that now we have an equation which is in terms of Q, quality of the feed, which is given to us. So we can write down this expressions or this expressions. All right. Now let's consider again two operating lines. So right now we want to draw this Q line. Okay, we will see what is Q lines. So we have the equation of the operating line in two sections. Yg equals Lx plus dxt. Notice, the same as all we have done, we have written as y equal L by G plus we had d by G. So we have written in different form. So this is the operating line equation for enriching sections, and L by G is same as R by R plus 1, etc. Or we have here xt by R plus 1. Okay. So it's a different way of writing this. So this is the operating line equation for enriching sections, and we can also write operating line equation for a stripping section as Yg bar equal to L bar minus X minus W XW. All right. So again here one can write, or earlier we wrote Y as L bar by G bar. So all we have done, we have multiplied by G bar, and we have W over G bar. So different ways of writing the two operating line equations, either in terms of reflux ratios or in terms of L and G, or L bar and G bar for stripping sections. Okay, so you should be familiar with different ways of writing it. So if you have these two equations, now if we subtract, you can show that G bar minus G into Y. So look at this, G bar minus G. This is how we are going to get the Q line equations. G bar minus G same as L bar minus L X minus W XW plus dxt. All right. You should be able to recognize immediately this WXW plus DXD is nothing but FZF. All right. So this is what we had, FZF, and we have the top product DXD or YD, and here we have W and XW. So this term is written like this. That means, and G bar minus G, recall we can write FQ minus 1. L bar minus L we can write as QF, and this term we are writing as ZF. So as an exercise, just takes a minute to rewrite this equation as Y equal to Q by Q minus 1 X minus ZF over Q minus 1. All right. So this is what we call it, Q line. This is Q line here. Okay. So what is this Q line? One can also interpret from this way, that this is the intersection of the two operating line curves. All right. So we started with the first line, this equation for enriching sections, second equation for stripping sections. Subtract, make use of this balance, nothing but a molar balance for the feed plate. All right. G bar minus G will be FQ minus 1. L bar minus L is equal to FQ into F. if we have saturated liquid, Q is 0. All right, if you have saturated liquid, then Q is 1, excuse me, all it means L bar will be equal to L bar plus F. So everything is liquid here. Similarly, if you have saturated vapor, okay, then you can say that you have Q equal to 1, etc., and you can entire vapor which gets converted into G bar. Okay, so we have these equations for Q line, which we'd like to plot on y-axis diagram. So we have this y versus x diagram, and we have this 45-degree line. We have this equilibrium curve y versus x, and we start with here as usual xt. We have a straight line for the operating curve with the slope, with the intercept, etc. Start from xw, you take another operating line here. Okay, now we want to mark this feed line, Q line. So go back to this equations, which we should write here again, y equal to Q over Q minus 1 into x minus ZF over Q minus 1. And here, like in the previous case, if we substitute x equal to ZF, we should be able to get y equal to x. Right? So all it means y equal to x equal to ZF. All it means ZF line coordinate, this also satisfies this operating line. That means from ZF, if you draw with this intercept with the slope of Q minus 1, Q over Q minus 1, or intercept of minus ZF by Q minus 1, one should be able to convince that this line will be passing through this. So this is your ZF mark. You come to this 45-degree line and take the slope of this line as Q over Q minus 1. This line will pass through the intersection of operating curves, this and this, because we obtain this line. So as an exercise, you should be able to draw the graph and convince yourself that this Q line with this slope will pass through ZF as well as the intersection of these two operating lines. So there is no need to go to this intercept of ZF Q minus 1 negative to draw this operating line, although this is possible. Okay, so all we have, we had L bar as L plus QF. Q is 0, L bar equal to L. Everything is vapor phase here. And we have G bar as G plus F Q minus 1. So if Q is 1, so everything is G bar equal to Z. That means it's a saturated liquid. So, all right, so Q can take any values 0 and 1. That's why it's called quality, state of the feed. It decides state of feed. And from this, if you divide, then you should be able to get L bar minus L, G bar minus G, so that this is your Q over Q minus 1, slope of this Q line. All right. So what does it mean? If I redraw this curve, equilibrium curve, y versus x, 45-degree line, and now what I do, I start with xt, take the slope of r by r plus 1 or intercept of xt by r plus 1, and then I take this now ZF, draw this Q line with the slope of Q over Q minus 1. We know this Q line intersects this 45-degree line where we have ZF equal to y. So this point, if you just draw with the slope, this will intersect here. If I connect this xw, I have the operating line equation for this stripping sections. All it means, to obtain, we have three lines here: equation of enriching section, equation of operating line for this stripping section, and we have this Q line. If we know two, we can find the third. Suppose I start with x at w, I draw this slope as L bar over G bar. I know this operating line intersects 45-degree line at x equal to y equal to xw, and then I connect with this operating line, and from the intersection, if I connect this to 45-degree line at xt, I should be able to obtain the operating line equations with the intercepts of xt by r plus 1 with the slope of r over r plus 1. So this is all expected because we have three equations. The third is intersection of the operating line for the stepping section and the enriching section. So fix any two, 1, 2, you get the third. You fix these two, you get the third. You fix these two and connect with this ZF, you will get this Q over minus 1. So let's sum up what we have done here. All right. So going back to the second McCabe-Thiele method, we work on y versus x diagram. All right. Then we have xt and we have this xp. All right. So from xt, if I draw an operating line, and with this q line, I draw this, ZF, I draw this q line. Wherever it intersects, from there, if I connect with xw, you should be able to convince yourself that this is the operating line equation for your stepping sections. All right. Similarly, if you start with the q line, intersects, draw this operating line for the stepping sections. Wherever it intersects, you connect to this x, y equal to x corresponding to xt, you should be able to convince yourself that now you have obtained the operating line of this enriching section. In other words, we just three equations, knowing two will give you the third. Okay. Now let's see what are the values. We talked about this q as a quality of feed. Q can assume a values between 0 and 1. So you have a saturated liquid at the bubble point. You have saturated vapor at the dew point. All right, so two extreme cases. Or you can have a feed which consists of liquid plus vapor. All right. So what happens if a Q assumes different values, or what happens if the quality of the feed is different or varies from one end of saturated liquid to another end of saturated vapor, or in fact you can have superheated vapor, you can have subcooled liquid below the bubble point and greater than your dew point. Okay. So we will like to draw different types of Q line here for our better understanding. So we will draw again this y versus x curve. So every time we have this McCabe-Thiele methods, we have y versus x. Unlike in Ponchon-Separate methods, we had hx, yx diagram. So we have xt here and we have xw. All right. We understand. We draw two operating lines anywhere, Q line will be fixed. Okay. So what we do here, let's assume that we know the reflux ratios from the total condenser. Let's assume it's the total condenser. So the vapor phase composition y1 same as xt, same as what goes to the top plate as x0. All right. So all three are the same. Total condenser. We know the reflux ratios are as L0 over D or L over D. All right. So with this xt, now we draw this operating line. Okay. Now let's assume case 1. If feed is saturated liquid, all right. So if the feed is saturated liquid, now again you should invoke on the definition for Q, which we had earlier, Q as L bar minus L over F from the material balance, and from your enthalpy balance or energy balance we had Hg minus Hf over Hg minus Hl. So if the feed is saturated liquid, it's all at bubble point, Q is 1. All right. So we are talking of Q as 1 because now we have entire liquid. So there's a feed plate here and this feed enters here. We have the vapor, we have the liquid L bar, we have L, we have G, and we have G bar. So if everything is saturated here, all right, saturated liquid, then Q is 1. All it means, of course, Q over Q minus 1, this will be infinity, and entire L bar is L plus F. Okay, so L equal to QF plus L bar. Q is 1, L bar is L plus F. So entire liquid was saturated, entire feed was saturated. So whatever L we had liquid flow rate from the top column, entire liquid goes into this. So this is a schematic of your first situations where we are saying that the feed is saturated liquid. Q is 1, Q over Q minus 1 is infinity. So now let us mark ZF. So these are feed compositions. All right, so this is your F, this is your ZF. All right, if we talk of this enthalpy, HXY diagram, straight line, we are talking of this liquid which is right here. This is your HF. HF is same as your HL. Okay, so a saturated liquid, L bar equal to L plus F. Slope of this equation, slope of this operating line, Q line is now infinity. Q is 1, which means now we have this Q line going vertically up. So this is your Q line. And in that case, the equation of this stripping section line will connect like this. So this is the case 1 or A, saturated liquid. The second case we will expect is if all feed is saturated vapor. So if all the feed is saturated vapor, we are saying that Q is 0. All right, because similar to these equations, we also have Q minus 1 as G bar minus G over F. All right, so keep all these two equations together. This is how we got the equation of Q over Q minus 1. If we divide this, we obtain this line here. Now if the feed is saturated, Q equal to 0. All right, all it means Q over Q minus 1 is infinity. Okay, sorry, this Q minus Q is now 0. Which means from here, if we draw this line, ZF line, then this line will go horizontally. All right, so let's redraw the case B, where we are saying that if we have feed is saturated vapor. So Q is 0. Q over Q minus 1 is 0. All right, which means G bar equal to G plus F. We have minus 1, or we are saying that G equal to G bar plus F. So let's go back to this feed plate. Feed is saturated vapor. This is L. This is L bar. All vapor gets into this vapor phase. All feed gets into the vapor phase. So we have G and we have this G bar. All right. You can also write that G equal to G bar plus F, or L bar equal to L. That's what you will expect. If everything is a vapor here, vapor phase, saturated vapor, then all vapor will get into this vapor phase, leaving this feed plate, and the molar flow rate of the liquid will remain the same here, L equal to L bar. All right. Now if we draw this on this Q line, well, we are saying that we have this operating line is fixed starting from XT, and at XF or ZF, mole compositions, now we have horizontal line like this. So this is your Q line. Q over Q minus slope is 0, so we have horizontal lines. Or on this YXY diagram, we can draw like this. This is XT, and if we have this XF, then we have this horizontal line Q over Q minus 1, and the intersection, if you connect with xw, you will get this steeping line equations. So we have two situations here, feed is saturated vapor and feed is saturated liquid. We can also, and this, if you go back to this hxy diagram, or we are saying that now the feed is here. This is your hg curve, this is your hl curve, and feed is saturated. So the first case was feed was cold, saturated liquid here, and the feed was, second case, case number B, is when the feed is saturated vapor. Let's take second case. C, call it cold feed. Okay, so what we are discussing here is a feed which is, whose temperature is below bubble point, or we can say that HF is less than HL. So going back to the definition of definition for Q, we have Q equals Hg minus Hf over Hg minus HL, which is from material point material balance L bar minus L over F. Q is greater than 1.0 because Hf is smaller than HL. All right. So that means the slope of this Q line, which is Q over Q minus 1, will be greater than 1.0. So if we plot, let's say this is 45-degree line, this is XD, here this is XF, and we have XW. This operating line is, slope of the operating line is greater than 1. So it will be something like this. We have one operating line and the second operating line which will intersect on like this. So this is your Q line. All right. This is, you can write, this is your 45-degree line on your graph paper. The second case, or the D case, will be hot feed. So what we are trying to say here, that HF is greater than Hg. So it's a vapor phase here, which means, going by the same definition, Q is less than 0, and the slope of this Q line will be Q over Q minus 1. This will be greater than 0, you can see yourself, and but less than 1.0. So in other words, in this case, if we plot, if we take again this 45-degree line, and let's say this is again XT, this is XF, and here we have XW. Now the slope is greater than 0 positive, but it's less than 1. This Q line will have a slope something like this, all right, with the operating line connected to this and this. So this is your Q line. This is the Q line right here, okay, with the slope Q by Q minus 1. The last case would be mixture of liquid and vapor. So essentially we have HF less than Hg, but it's greater than HL. So we have mixture of both vapor and liquid. Feed consists of, you can say, GF vapor and the liquid. In this case, Q is greater than 0 and is less than 1, and one can show that this Q line's slope will be nothing but LF, the amount of liquid in the feed, over LF minus F. All right. In this case, the 45-degree line is like this, XT, we have XF, we have this XW, and if we draw this line, this operating line is something like this, with the Q line is like this, all right, with the operating line like this. So this is the Q line, all right. So these are 6 cases, A to E, we have discussed in this lecture. What we should discuss next is the location of feed tray. In other words, at what locations, what tray, which the feed should be enter. So we have the trays like this, at what location the feed should enter this distillation column. So we have this location of feed tray. All right. So essentially we are looking for introduction of feed. Okay. So in this case, let's take one of the conditions, one of the situation where we have, let's say this is yx diagram and this is the two operating line and this is the Q line. Okay. So to draw the states, again we start from xt, the top distillate composition. So we go to this equilibrium curve, we come down to this operating line, top plate of the top column, then we cross to this. Okay. So once we cross this Q line, then we are supposed to switch over to this second operating line, the operating line for this stripping sections. All right. So essentially here we switch over from the top operating line to the bottom operating line, which is operating line of rectifying section, stripping sections. Once we go at Q line, so once we cross this Q line, then we are supposed to switch down to this second operating line. Okay. So and the second case would be we can delay the feed entry. All right. So we are trying to say here that if we have this equilibrium curve like this, let's say we have this operating line for the top column and we have the operating line for the second column, then we start drawing this tray, go to this operating line, and this is the Q line. So we are trying to say here that we can still continue marching on the top operating line, and then we can come down to this second operating line. All right. So what we are trying to say here that in this case we have this late entry. If you like to expand this here, so we have the two operating line, we have this Q line here, and if you're starting from say xd, come to the equilibrium curve, then even if you have gone past this Q line, one can keep on marching on this. Right. So this is the equilibrium curve till after some time, you can reach almost the point of pinch, and then you can come down to this second operating line. So here we have delayed feed entry. All right. So this is a case 2 where we have delayed feed entry, and then we can also have what you call early entry. So if you again draw this y versus x diagram, okay, so let's say you have yx diagram like this, start from xt, okay, so xt like this, start from xw, you have second operating line like this, this is the Q line. There's a possibility that you can have early entry, which means if you go like this, come to the first one, come to the second, but now before the Q line one can switch down to this second operating line. So even we could have delayed here, say stage 1, stage 2, and we could have delayed to the third stage, but now we can switch to the second operating line even before this Q line, right. So here we have this early entry. Okay. So let's make a point here that the three ways of, suppose you have a new distillation column which you want to design here, then there are three possibilities. of locating this feed. At what feed tray we should have the entry. In one case, even before this Q line, one can switch down to the operating line number 2 for this stripping column. In one case, we can have the early entry, so that's where we have the Q line. We start from drawing the trace stages. You have the options that before Q line or after Q line. In some cases, it's possible that you switch down to this operating line for the stripping sections. But the most optimal number of or minimum number of plates, one can show that you will get it where you have the opportunity, the first opportunity to cross this Q line. So all it means that even if you have not violated this enthalpy balance or the species balance or the total material balance, there is a flexibility of adding feed, say between number plate 3 to 5. In one case, one can switch to the second operating line at the plate number 3rd. In one case, you have the options for switching at number 5. In one case, you have the options at Q line, just going past the Q line at plate number 4. So one has a luxury of entering the feed between 3 to 5. So as we said earlier, that mostly for a new distillation column, one would like to have a minimum number of plates. Okay, so in that case, it happens that one should try to switch down from operating line for the rectifying section to the stripping sections at the first opportunity where it goes past this Q line. Okay, so these are the 3 different ways of entries. Now what we do here, just like in the case of Ponchon-Sevret, we try to find out the minimum number of plates corresponding to the total reflux or the infinite reflux ratios, and the second case when we had this minimum reflux ratios, when we have the infinite number of plates and infinite number of this condenser load or the boiler load. So these are the 2 different situations we will address here. Okay, so what we are trying to say here is condition 1, when we have this total reflux or what we call infinite finite reflux ratio. So all we are trying to say that if the reflux ratio is defined as R equal to L by D, we will like to monitor the slope of the curve with increasing L by D and see what happens to the number of plates here. All right. So the slope of the curve is L by D, L by G. All it means that when we take the limit R tends to infinity, we have L by G equal to 1. So you should be able to show that the reflux ratio is nothing but slope of the curve is nothing but R over R plus 1. So when you take the limit R tends to infinity, the slope becomes 1. All it means the operating line will coincide with 45-degree line, diagonal line. Okay. So physically all we are trying to say here that when you have the distillation column and we keep on increasing this reflux ratios till it's whatever we have infinite reflux ratios, so there is no top product withdrawn here. In that case, if we have very large amount of liquid flowing through this, even at the bottom product, entire vapor has to be sent back to this distillation column to the reboiler. So essentially this feed has to be switched off and we have this liquid entire reflux circulating within this distillation column. Suppose it's a hypothetical case, but these conditions will give us minimum number of plates. So the idea is that we should see geometrically or graphically what happens to the locus of intersection of the 2 operating lines or the slope of the 2 operating lines. So if we have this y versus x curve and we have this operating line, then if you increase the slope, all right, so when we are saying that reflux ratios is R over R plus 1 and we increase the reflux ratios, so the slope increases. All right, so R equal to R plus 1 is the slope, or L by G slope increases. So which means if this is the Q line, fix the Q line, you will see that now we are tracing the curve like this. Slowly and slowly the slope is increasing. The 2 operating lines, they approach 45-degree lines till at infinite reflux ratios. When R is infinity, we have R over R plus 1 reaching 1. This is the equilibrium curve here. two operating lines have coincided with this 45 degree. All right. So in this case, the construction of number of stages, all you have operating line, you do the same thing what we did earlier, from starting from xt go to y1, right, or x1, y2, etc. Since you have the operating line coinciding with this, you get minimum number of plates. Minimum number of plates. And in this case, since operating line is now y equal to x, right, one can obtain analytical solutions for minimum number of plates if we have certain assumptions like relative volatility of A over B is constant. So in this case, one can do some calculation here. So what we want to do here is that we have y equal to x, so that's the equation of this operating line, equation of the operating line at infinite reflux ratios, and if we assume relative volatility alpha is constant, then recall the definitions for alpha AB as y over x over 1 minus y over 1 minus x. So we can write y over 1 minus y as alpha x over 1 minus x, and starting from xt, one can start substituting in equilibrium curve and operating line alpha. So we have x1 1 minus x1, where we are obtaining this y1 from xt. So starting from xd, we have y1, that's the operating line, and once y1 is in equilibrium with x1, so we have the situation that this is xt, and the top plate we have y1, and we have this x1. All right. So by making use of operating line and then this equilibrium curve, we can have set of equations like y2 over 1 minus y2 alpha x2 over 1 minus x2. Similarly, we can write here xt over 1 minus xt equal to alpha. Keep on substituting one equation to a second equations to have nm plus 1. All right, xw over 1 minus xw. Essentially, where we can obtain analytically the expression for nm plus 1. So 1 signifies here the reboiler which we have at the bottom column. So nm plus 1, minimum number of plates at infinite reflux ratios when the relative volatility is constant. One can obtain an analytical expressions. Log xt over 1 minus xt, 1 minus xw over xw over log alpha a beta, and for better accuracies, alpha a b generally taken as the geometric ratios of top product at the and for the bottom product, and this equation is well known and known as Fenske equations. All right. So as an exercise, you can try this. Start from your top column, xt, then y1 x1, then you have y2 x2 in equilibrium. So every time you write down this equilibrium curve equations for this, and for the operating line you have every time you're writing this y equal to x. So with these two equations, successive substitutions, one can obtain an expression for minimum number of plates, including this reboiler, as the ratios of known quantities like top product, top composition, bottom composition, and the average relative volatility. Okay. So this is what we have for the total reflux. Similarly, we have the second case when we have this minimum reflux ratio. So now we will do the same thing. When the reflux ratio decreases, then the ratio also, the slope of the operating line also decreases, right? Or L by G decreases. So here again we will do the same thing from y over x diagram. We will monitor the slope of the two curves. So a general case would be when we have intersection like this equilibrium curve. Now when you decrease the reflux ratio, the slope decreases or L by G decreases. You can make out that now the point will move upward. All right. So this is, if you try to extend here, enlarge, then you have this Q line, and two operating line intersects here at minimum reflux ratios, or as the reflux ratio decreases, then the slope will decrease and this point will move upward till it makes pinch with the equilibrium curve. So if you take this line here, line this here, you have this pinch, all right, where the driving force is 0. So corresponding to this, if you extend, this will give you minimum reflux ratio. So you have essentially slope of this curve R min, it comes from intercept, from the intercept you get xt over R min plus 1. All right. So this is the intercept. From this one can calculate minimum reflux ratios. So at this minimum reflux ratios, you have infinite number of plates. So here the number of finding this minimum reflux ratio or the maximum reflux ratio is the same. You start with, fix the Q line. You know the composition of the two curves. So you have an, say, general operating curve like this. In one case, you must have noticed that slope increases like this till it makes a coincides with this 45-degree line. In one case, it's moving upward, all right, like this, like this, like this, till it makes a pinch here. Okay, so that's the argument for minimum reflux ratios and the maximum reflux ratios. From this R min, generally one get infinite number of plates, but the operating reflux ratio is generally, typically it's 1.5 times R minimum. That means again you choose this, the ratios RD, RP equal to 1.5 times, and one can reconstruct the equilibrium curve. So now we have this intercept as R plus 1, where this R is 1.5 times the R minimum corresponding to this pinch curve here. All right. In this case, there is one small thing to discuss here, that we can also have some non-ideal situations in which y versus x diagram may not be necessarily concave downward all the time, which means there could be an equilibrium curve like this. All right. In this case, if you start from xt looking for this minimum reflux ratios, it's possible that this operating curve can make a tangent, all right, much ahead of this pinch here which occurs here. All right. So in this case, just like similar to this what absorption curve we have, one has to draw this pinch here, make a tangent wherever it makes a pinch with the operating curve. So if you have the slope like this and you are starting from here, then look for the tangent with this equilibrium curve here. Unlike in the previous case, we said that let's make an intersection of the two operating lines at this equilibrium curve. So in this case, one has to see that where this operating line, it makes a tangent with this equilibrium curve. So that's the point where one should take this R minimum. So if you take the intercept, this will give us xt over RD plus 1. So from here again we take 1.5 times etc. R operating equal to R minimum. So very often when we have this pinch, then one has to be a bit careful and look for this shape of the curve where the operating line can make a tangent. This is very similar to what we did in case of absorptions. All right. So today's lecture, we will like to summarize that now essentially starting from Q line, we can Q line and one of the operating lines, we can draw the second operating lines, or we can take the two operating lines and can draw this Q line. So out of, we have three operating lines equations. One is a Q line which came from the, or which we obtained from the energy balance, and we have the two operating lines which we obtained from species balance. So knowing the two, the third can be found. And then we can do this construction of the trace. And we said that as a general practice, the feed entry is always very often it's at that locations where we have the first opportunity to step down from the operating line for the enriching section to the operating line for the stripping sections, just past this Q line. Otherwise, there is always a latitude, there is a luxury where you can have an early entry or when you can have late entry. But that gives you a larger number of plates than what we will get in case of optimum line. So then that's the one thing. Then we had the two general scenarios of infinite reflux ratios, and we had the second one where we had the minimum reflux ratios, which requires infinite number of plates. And in this case, all we have to do is to monitor the slope of the two operating lines as the reflux ratio increases or decreases. So when the reflux ratio increases, we saw that these two lines, operating lines, coincide with this 45-degree line. That time you get minimum number of plates. And if the constant, if you have the mixture, you can assume that you have a constant relative volatility. One can get analytical expressions for minimum number of plates. We call it Fenske equations. So that equation you should be able to drive on your own as an exercise. All you have to do is that operating line is now simplified, y equal to x, and then you have equilibrium curve in terms of alpha relative volatility between y and x. So you can have successive substitutions, use operating line, then equilibrium curve, then operating line, equilibrium curve. One can obtain this Fenske equations. In case of minimum reflux ratios, we try to decrease the slope, in which case the two operating lines makes a pinch or intersects at the equilibrium curve where the driving force is 0. Then we can obtain, we can see that we will get infinite number of plates. So there we get the intercepts of this operating line or the slope also that will give you R min. Generally distillation column we have 1.5 times, very similar to what we had in case of absorption columns. So now we get the new reflux ratios. Based on the new reflux ratio, we have the new operating lines, and then we can find the number of plates. We also said that when very peculiar situations where we have this acid drop or we have non-ideal solutions, then one has to watch out for the operating line making a tangent with this equilibrium curve at some point other than where we have this intersection of the two operating lines at the equilibrium curve. So in that case, we get this R minimum at a slightly smaller reflux ratios. So from that we get R min. Again, we take 1.5 times. We construct the y versus x diagram with the equilibrium curve and the appropriate operating lines to find the number of plates at some stages. So this today it's the end of this lecture. Next time when we meet, we will have one example based on McCabe-Thiele method.